In the last part of the series, we saw how character encoding went for a toss when people from different regions speaking different languages, started encoding characters to suit their language. And the whole process of communication using computers sort of broke down, with file transfers and emails, etc., across different regions and different languages. So the Unicode Consortium came into picture, which was a group from different countries and companies whose job was to encode all the characters that exist in the world in a way that there are no clashes. Now, in the beginning, Unicode started with a fixed width 2-byte character set, but it soon fell apart and is not in use anymore, okay? But that has led to a myth that Unicode characters are all 2-byte characters, okay? But that is not true, as you will see in this tutorial. Now, during the ASCII days, characters were mapped to integers. And because we were using a single byte to represent characters, there was hardly a difference between the integer that the character was mapped to and its representation in memory. At least that was not discriminated consciously. For example, the character A was mapped to the integer 65, which in binary was represented as this in a byte. So saying that A is mapped to the integer 65 or saying that it is mapped to this binary sequence was kind of one and the same thing. But Unicode approached this problem differently. They said, let's first map all the characters to integers, okay, which are just numbers. And that is step one. But how we represent these integers in memory or how many bytes to use to represent this integer is altogether a different thing. For example, A could be mapped to the integer 65, which is called its code point. So 65 is the decimal code point, while 10000001 is the binary code point for the character A, and we have not represented it in memory yet, okay? But when we define how to represent it in memory, that leads to different encodings, which are all Unicode encodings. And this is a very crucial idea, okay, because now if an encoding has some problems, it can be phased out or discarded in favor of a better one. And that's how we see that there are tens and hundreds of Unicode encodings, some of them being minor variations of each other. But UTF-32, UTF-16 and UTF-8 schemes have become the more popular ones, and out of these three, UTF-8 has almost become the de facto encoding scheme for web applications, and for good reasons, okay? In this tutorial, we'll touch upon these three encoding schemes, and it's not going to make you an expert, but you will understand enough what's really going on behind the scenes, especially if you work with databases or are a software or web developer. In this part, we'll talk about UTF-32 and UTF-16. So let's get started with UTF-32. Now UTF-32 scheme said, let's store the integer in 4 bytes or 32 bits. So it is a fixed width encoding scheme because the number of bytes to store the integer is fixed. Now this code point represents the character A. So how do we store it in 32 bits? Well, it's very easy and straightforward. We store it like this. And this is the memory representation of the code point for A in 32 bits or the UTF-32 encoding scheme. Here we fill all the bits of the code point from the right side and fill all the remaining bits with zeros. This is very simple, straightforward, one-to-one mapping and should have been widely used but for one big problem. And the problem was that the English-speaking world didn't adopt it widely because for them, each of the characters needed to be converted to 4 bytes from one single byte. And that would mean that if there was a file of size 1 KB, containing only ASCII characters, it would become 4 KB in UTF-32 without adding any more information. Not only will it affect the data transfer times, it's actually a huge wastage of memory, okay? Moreover, porting all the existing data to the new style of encoding itself was a huge deal. So UTF-32 sort of took the backbench. Now, this is a pure engineering problem, okay, to be able to have something which works for all the existing stuff as well as the new characters that are known or will be known later, which are yet to be encoded. So, another solution in the form of UTF-16 came up. Many people think that as UTF-32 is a 32-bit character set, UTF-16 is a 16-bit character set and UTF-8 is a 8-bit character set. But that is not true at all. In UTF-16, the code point may be represented either in 16 bits or if required in 32 bits. That is either one chunk of 16 bits or two chunks of 16 bits. So this kind of character set is a variable length character set because the width of bits in memory is not fixed. Now, what is the advantage over the fixed 32-bit representation? Well, at least for ASCII, the size of files will not be 4 times, although they will still be twice the original, and it is still not backward compatible with ASCII. That is, a file containing ASCII characters in the old ASCII format will still need to be converted to UTF-16 encoding if some software wants to read it as UTF-16. This point will be more clear to you when we talk about UTF-8 in the next part. By the way, let me point out that the Unicode code points have been mapped in such a way that the first 127 integers are mapped to the same characters as in ASCII. So how do we represent this code point for A in memory using UTF-16 encoding? Well, this binary representation can fit in 16 bits. That is, we will not need 32 bits in this case. So we can fill the first byte with all zeros and the second byte with the required bit sequence. Now here I have used hexadecimal numbers to avoid using up a lot of space, but essentially we are saving the same number. 41 in hex is equal to 65 in decimal. And if you are following along using a notebook, you may want to expand this whole thing in binary as follows. So the box with a blue background represents a bit, while the box without the background color will represent 8 bits or a byte for this tutorial, okay? We mostly use hex numbers in the world of computers as a short form of binary because that saves us some writing by 4 times. If you don't quite understand hexadecimal number system, you may want to check the video on binary numbers which explains the basic idea of a positional number system. And I think if you understand the basic idea of using symbols or digits at different positions to represent a number, you will have understood all kinds of positional type of number systems, binary, hex, oct being a few of them. Anyways, so we can represent the code point 65 in 16 bits as this. But is this the only way? I mean, can we not represent it like this? That is, we start storing from the most significant byte first. And it does kind of looks counterintuitive. That is, why would anyone want to do that? But as soon as Unicode said that, we'll use 16 bits or 32 bits for UTF-16, companies in their eagerness to say that their hardware or software supports the latest UTF-16 started using both ways of encoding. That is, some companies used the first format while the others use the second way. And of course, to us, it may not make sense, why the second option is reasonable. So to put things in perspective, consider this. And remember that we were still in the C programming days when all these things were going on. If you are familiar with C programming, you would know that one would write this kind of a code to get an array of integers of size 6. And the address that the operating system returns would be that of the first byte. So the variable ptr_1 points to the first byte in the whole sequence, and the way memory is laid out, all the subsequent integers can be accessed by just incrementing the previous memory address. So if data is stored in 2 bytes, we will need to store it as an array of 2 bytes, isn't it? Because during the C days, we either had a char data type, which was like a byte or 8 bits, or we had an int data type, which was, well, usually 32 bits. So the pointer would point to the first byte, and if we know that it only contained ASCII text, which was quite a common case in those days, to be able to read the data, the pointer must move to the second position in the first case, while it could be read immediately in the second case, and then one could go to the next character. So the second format seemed to be more efficient for certain kinds of operation, both at the hardware and the software level. The first form came to be known as the little endian because the data is stored in the least significant byte first, while the second form is called the big endian form of UTF-16 encoding because the data is stored in the most significant byte or the higher order byte first. Alright? If you didn't understand the memory and pointer stuff, it's alright. You just need to understand that there are two forms in UTF-16, the big endian and the little endian, which is yet another problem and causes a great deal of confusion. Also, for people using ASCII, if they adopt UTF-16, their data size would still be doubled. Now, what is the problem of having two different types of encodings for UTF-16? If you had to read a sequence of characters in a file and we are told that the encoding is UTF-16, will we be able to read the file? Well, not quite, One has to know whether it is in the big endian or the little endian form. So to hint at which type of encoding it is, an additional non-character data was added at the beginning of the file, which could be 255 followed by 254. And this is called the byte order mark, telling how the bytes are ordered in the file. So for little endian form, the 254 data is saved in the least significant byte, and in hex it can be written as FFFE because in hex FF is 255 and FE is 254. Whenever we write a number starting with 0x, it means the number is in hexadecimal form, okay? And most of you would know that anyways. And if the data was in the big endian form, the byte order mark will be this, in which 254 will be saved in the most significant byte, which in hex can be written as FEFF. By the time the idea of BOM or byte order mark came into picture, there was already enough data in both forms without the BOM. So having a byte order mark is not mandatory for backward compatibility reasons. And in case a software parser does not find the byte order mark, it will assume one of the two, big endian or little endian, try to pass the data, and if it encounters errors, it will assume the data is in the other format and will try passing it again. So as you can see, it became quite complicated with all sorts of tricks needed to just keep it from busting. So another encoding was required, which came as UTF-8. And that saved the day for us. And we will talk about it in the next part. But before that, you may want to try out the quiz, just to make sure that you got the basics.